Right, we started chapter 17, and with today's lecture, we will finish it. And it's about current and resistance, right? So first section started with defining the current. So what is current? How did we define? Yes. No, really. Charges, moving charges. If the charges are moving, it is current, okay? But the correct definition is we use the symbol I. Is suppose there are this many coulombs of charges are flowing, divide by the time, we stop at the cross-sectional area and passing current, we count it. Charges, we see how many charges are flowing, how much charges are flowing, divide by the time it takes for them to flow, make that flow. The rate of flow of charges is the current. Okay, it's a coulomb per second, and we have a name for coulomb per second, which is current. It's coulomb per, I mean, coulomb per second is the unit, but we have a single name for coulomb per second. We don't keep saying coulomb per second. Instead, we say current is the unit. Coulomb per second is the unit. Okay, but we have a one name for this, coulomb per second, as a unit. What do you call coulomb per second? What is the other name for coulomb per second? Yeah, you don't say, no, not volt. Voltage is the potential difference. What do you call coulomb per second? What is the other name? One name, like, kilogram meter per second square. That is, we call it, this is the force, right? The unit for force is kilogram meter per second square, but we have a single name for that, which is Newton. No, I mean, I'm talking about this now. That's Newton. Similarly, coulomb per second is amperes. You said that? Maybe I didn't hear you. Sorry. Okay. He said that. Yeah. Okay. Amperes. Yeah. Okay. Okay. Good. Good. Then in the section 2, I'm just going through what we already did. Okay. In section 2, we looked at the microscopic view and we derived this relationship between the charge, between the current and the drift speed of the current. The charge carriers, like in a copper wire, in a conductor, excuse me, please, quiet, are electrons. The charge carriers are electron in a conductor, and the current is due to the motion of this electron, and the speed of this charge carrier, we call it Vd, the drift speed, and the current are of course related to each other. So where I is the current and Vd is the drift speed of the charge carrier, and you should know what the others stand for. This is the density of the charge carrier. This is the cross-sectional area through which the charges are flowing. And this Q is the charge of one charge carrier. So for example, if it is an electron, which is the charge carrier, the charge of one electron is that Q. Then we looked at measuring current and voltage in electric circuit. Then we defined what is resistance and the Ohm's law, which relates the current and the voltage. That's where the resistance come in. We made the symbol R for resistance. And also we introduce this resistivity, which is a constant for a given type of material. In section 5, that is where we stopped. We covered that. The temperature variation of resistance, where we had a formula which gives you how the resistance varies with temperature for typical certain conductors, metals or the resistance actually decreases with temperature. Okay, and let's go to where we stopped. Okay, now the next section is of about electrical energy in a circuit. So in a circuit, there is current. Okay, in a closed circuit, if it is connected to a battery, a source of power, like a battery, there will be a current. Current means charges are flowing. So as the charges moves through the circuit, through the battery first, what happens when the charges are collected at the positive end of the battery? Well, the electrons move in the opposite direction. Electrical potential energy of the system is increased by this much of amount, where delta V is the potential difference or the voltage of the battery, and delta Q is the charge which is going through the battery. So, this is the change in the potential energy. So the energy that it gains as the delta Q charge move from the negative end to the positive end is given by this equation. Where is this energy coming from? From the battery. So there's a chemical energy of the battery because there's a chemical reaction which makes the charges to flow. So we can say it is the chemical energy of the battery which gets turned into the electrical energy. Now, then the charges do not stay there. Suppose we connect the battery to a resistor. The charges, as it moves through the resistor, it will lose its electrical potential energy during collision with the atoms in the resistor. So through the resistor, as the current flows, the resistor will become heated up. That's because the electrical energy is now turned into heat energy as the current flows through the resistor. The temperature of the resistor will increase. So here we have drawn a picture of a simple circuit. This is the battery and this is the resistor. So let me put some points, the negative end of the battery as A and B, and we connect the end A, the point A, to the ground. So let's make the potential here at 0. So suppose the battery has a potential difference of 1.5 volt. The negative end will be at 0 volt and the positive end will be at 1.5 volt. So as the charges move from A to B, it will gain an electrical energy given. So as a charge delta Q move from A to B, it will gain electrical energy from the chemical energy of the battery. So we take the point A as the reference point, that is by connecting it to the ground. So we can say it is a 0 level. Now, as the charge move from the battery from A to B, the potential energy of the system is our circuit, increased by this amount, delta Q, delta V. And where is that getting the energy from? From the chemical energy of the battery. So this means the battery would have lost that much of energy from its chemical energy. So there is always, if they are getting an energy, it must be coming from somewhere. It is not coming out of nothing. Now, as this charge moves through the resistor, so let me draw it again. So you have the A and B. and I put this is the resistor. Here we have C and D. As the charge delta Q move then from C to D, what happened to the electrical energy now? It will be lost as heat energy, and the temperature of the resistor will increase. Now, as the net result is that the chemical energy from the battery has been delivered to the heat energy at the resistor. How do you know there is heat energy? If you touch the resistor, you will see it is hot now. Okay. So the energy is now transferred to internal energy in the resistor. So the atoms of the resistor now is vibrating faster. That is what you feel as hot, the temperature of that. When the charge returns back to A, the end of the battery, we can say the whole process is now complete. The chemical energy of the battery has been delivered to the resistor, and the temperature of the resistor has increased as heat energy. Now, power. You heard this word before in semester 1. We talked about power. Power is the rate at which the energy is transferred, okay, or work is done. That's what we do in the mechanics. Is the work is done. Work's done is the energy. Here we will say the rate at which the battery transfers the energy to the circuit element is the power. So energy is delta Q, delta V. If the delta Q travels between a potential difference of delta V, the potential energy change is given by that. So that is the energy delivered. Divide by time will give you the power. That's the definition of the power. Energy divided by time. So now if I group this delta Q and delta T together, do you recognize this? That is a rate of flow of charges. What we call that? Current. Current is the rate of flow of charges. So instead of delta Q over delta T, I put I. So this is the current. So power is now given as current multiplied by the potential difference. Now, this is the expression for power. Let me rewrite it here. Power is equal to I into delta V. Potential difference or the voltage multiplied by the current. We can give alternative forms for the power by combining it with the Ohm's law. Ohm's law is what? I can write it, delta V is equal to I into R. So if I substitute I into R for this, I will get another expression for power as I squared into R, because I and into IR, so it will be I squared into R. So we have alternative form for power as I squared over R. I can do one other thing. I can substitute for I from the Ohm's law as delta V over R. So if I put there, then I get this expression for the power. So instead of saying P is equal to I into V, I can also say it is equal to potential difference squared divided by R. So what is the point of all this? Sometimes it depends on the question. Maybe in the question you asked to find the power, but what is given is, say, only the potential difference across and the resistance. The current is not given. So in that case, instead of using that equation, I can use this equation. So depending on the question that you are given, you can choose one of the three expressions for the power. Okay, what about the units for the power? Power is energy divided by time, right? The rate at which the energy is transferred. So it must be joule per second. Okay, again in mechanics, we came across this. Power is joule per second. And again, we said before also, we have a single name for that, which is watt. Okay, watt. So it is after a person, a scientist, a physicist, and the symbol for watt is W. That is the SI unit for it's joule per second, but it has got a single name. Okay, so I must be in amperes and R in ohm and delta V in volts to get the power in watt. Now this unit for energy, the SI unit for energy is joule. But joule is, suppose you use up energy that is coming from the electricity board, you have to pay for the energy that you use, right? So 1 joule is a very, very minute, small amount of energy. If you are asked to tell me, okay, if you ask the electric company how many riyals I have to pay for 1 joule, the money will be very, 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 very small. Okay. So 1 joule is not a practical unit to charge for the energy consumption. So that's why we have got another unit, which is called kilowatt hour, not the SI unit, it's not joule. In fact, joule is watt second, right? Do you agree with me? Because watt is joule per second. That means I can say joule is watt into second, right? Because watt is joule per second means joule is watt into second. So look at this. This is actually energy unit because this is watt, that is power, and this is time. So power into time must be energy, right? So, but it is not 1 joule. But we can get the conversion. I can see what is 1 kilowatt hour mean, how many joules it is, because kilowatt means 10 to the power 3 watt. Agree? Hour mean how many seconds? 3,600 seconds. So we have, this means 1 kilowatt hour is 3.6 into 10 to the power 6 watt second. In other words, joule. Watt second is joule. So now we have the conversion between that big unit for energy. So it is 3.6 million joule is 1 kilowatt hour. So this is good enough, big enough unit for the electric company. Excuse me, please come to the front. Come to the front, please, the three of you. Why are you leaving? Come to the front, please. Come to the front now. Two of you. Both of you. So kilowatt hour is a energy unit, and it's a big enough unit so you can charge for that. It may be a fraction of a real still, maybe 1 real or something, but good enough. So that's why we need this big unit for measuring the energy. Now we come to the last section in this chapter, superconductors. Have you heard this word before? No. Yeah, it's a big news. I mean, well, in 80s, what do you think a superconductor is? A good conductor, right? Super good, yeah. Yes, yes. So any conductor, although we call it a conductor, it still has some resistance, right? A copper wire is a good conductor, meaning small resistance, but still has some resistance. You know, people found for some material called class of material called superconductors, below a certain temperature, its resistance drops to zero, just zero. Okay, simply. It's a kind of amazing thing because the applications are limitless, but the problem is we need to bring it to very, very cold. It's not practical. We are talking about this is in Kelvin. It is first discovered for, I think, helium when the temperature is below about 4.3 Kelvin. It's sharply dropped all the way to zero, but it is very impractical to operate at that temperature. We are talking about a temperature very close to the absolute zero Kelvin, minus 273 Kelvin, right? So that's why for a long time, although this is discovered in the 1900s, okay, for a long time, there was no, it is only theory. I mean, there's no practical application of that. We couldn't use it. But then comes, okay, let's talk about this superconductor a bit more. The temperature at which the resistance comes to 0 is called the critical temperature. So you need to remember this word, critical temperature. So it's also put this symbol TC, C for critical temperature for that superconductor. And this critical temperature depend on, because people started making superconductors by combining different material, okay, like copper or copper oxide and so on, mixing things and changing the composition. So they saw that by just changing the composition of different material, they can make this TC small, bigger. It's better to make it bigger, right? TC for say 4 Kelvin, by making some other material with a different composition, we can bring the TC up. If we can bring it to the room temperature, then we have, still it is not done. Very close, they have come very close to the room temperature. Room temperature in the sense that below 0 degrees still, but we are not there yet. The TC depends on the pressure under which the material is subjected to and the crystalline structure. So people play with this to bring a high temperature superconductors. Now, what about the superconductor? Once you set up a current in the superconductor, you don't need a battery to sustain this current, because the current just keeps flowing. The energy is not lost because the power is I squared R, right? R is 0. So the energy is not lost. Somehow we get the current going, say we connect the battery and get the current going, and the current will flow forever without any battery. The reason is resistance is 0. So this is the timeline for the superconductors. It was discovered in 1911, but as I said, yeah. TC, you know, the superconductor material becomes superconductor only below a certain temperature. Above that temperature, it is like any other resistor. Okay, so that is a critical temperature. For each material, the critical temperature is different. So people wanted to find a superconductor with a critical temperature close to the room temperature. Then we can have, you know, it can be a great breakthrough. Okay, we can have a superconductor that works at a room temperature. So in 1986, there was a big breakthrough. From here, we never got to have a superconductor high temperature. But in 1986, some people here cannot pronounce it correctly. Okay, just leave it. Near 30 Kelvin, it was thought a big thing because there's a big jump about 4 Kelvin to 30 Kelvin. You know, 30 Kelvin still mean minus 200 and something, right? It's a very small temperature. Still, it's not a practical thing. In the next year, people reach in the hundreds, 96, 105. Now, people get very excited, you know, when they. And currently, I think they are very close to. If someone can tell me what is the current temperature of a critical temperature of superconductors. I think 2 years back, there was a 2 years old, last year, I think. Almost room temperature superconductor, almost, not there, not exactly, maybe above 0 degree. It was a big thing. Right. So, yeah, if someone tells me to be nice, but let me continue. This is the last slide in the lecture, in the chapter. Superconductors. Here is a nice demonstration of a superconductor. What we have here is a superconductor kept inside liquid nitrogen. Now, let me go back a little bit. See, 96 Kelvin mean it is almost practical because we have liquid nitrogen. You heard about liquid nitrogen, right? When you liquefy the nitrogen, we can keep that at its boiling point, which is 77 Kelvin. 77 Kelvin is the liquid nitrogen boiling temperature. We can have it's practical to have liquid nitrogen. It will evaporate, but slowly. but we can have liquid nitrogen. The temperature of liquid nitrogen is its boiling point, which is 77 Kelvin. So if we have a superconductor with a critical temperature of 96 Kelvin or 105 Kelvin, you put that in liquid nitrogen, we have a superconductor. Okay, so that was a breakthrough here there in 1987. Okay, now what we see here is a superconductor. The one down is a superconductor kept in a liquid nitrogen, so it is a superconductor. The property of the superconductor is any magnetic field will be repelled by the superconductor. So if we bring a magnet, that magnet will be floating above the superconductor. So there will be a force which is trying to expel the, what happens, there will be a current flowing in the superconductor that will create the magnetic field that will oppose the magnetic field of the magnet that was above. So it will be levitating. Levitating means floating above it, yeah. So we have practical application of this maglev they have in German, US, where the train moves on a, it is not touching the railway track. So there's no friction, zero friction, not zero, air friction only. So it can go very fast. It's all possible because of the superconductor. It can create that much of magnetic field because of this property here. Okay, so that is the end. Now I will do some question from the past exam, but before that I will take past midterm that I have posted in Moodle. So I will take the question number 1 and we will try to cover all the questions that are of chapter 17. You'll see they are relatively very easy. All of them like direct question. If you know it, you know it. Okay, we have given the formula sheet as well. A typical lightning bolt. What is lightning? You know what is lightning, right? It is actually discharge of electric charge, right? It's actually a current because the clouds get so much charged and it reaches the break point. So even air become a conductor. It become highly charged, high voltage. So it can discharge electricity through to cloud or cloud all the way to the earth. So that's what you see as lightning. So here we have typical lightning bolt, which can last for this many seconds. And while it is discharging, this many electrons are transferred from the, say, the charged cloud to the earth. Calculate the current in this lightning bolt. So if there's a movement of these electrons through the air, it is a current. So he is giving us how many electrons are moving and in how many seconds it is moving. So we all have to do, the definition of current is the amount of charge divided by the time it took. He didn't give us the amount of charge, he only giving the number of electrons, but you know each electron has a charge. So you know the electronic charge is 1.6 into 10 to the power minus 19. Here we are being helped by telling you how to get the charge, but I may not put it there, right? If I'll only tell you this many electrons, then you should know how to get the charge. So it's a matter of substitution and divide by the time, and you get the current in coulomb per second, which is amperes. Number 2, in a certain material, there is 8 coulomb of positive charges per second flowing to the right and 8 coulomb of negative charges per second flowing to the left through a surface. Let me ask you, just leave that question aside. Let me ask you something. Let's say there is an electron and say there is a proton, which is positive and this is negative. Let's say this is going to the right and this is also going to the right. Let's say, okay, now forget about this question. I'm just posing you a different question. They are moving together. Do you think there is current? No, because it's neutral, right? Both of the, one is negative, one is positive. They are going together in the same direction. Is there a net current? If this is not there, there is a current. If this is not there, there is a current. So we can have current because of the flow of positive charges as well as because of the flow of negative charges. But you see what happens here, the effect cancel here. So that's why we have to be careful when you want to get the net current. In a copper wire, what is flowing is electron, negative charge, okay? But in a solution, okay, in an electrolytic solution, we can have positive ion flowing and the negative ion also flowing, right? So this is why we need a direction convention to define the direction of the current. When the positive charge is flowing, like say this one, the current due to this positive charge is also in the same direction. When a positive charge is flowing, the charge motion direction and the current direction is the same. When a negative charge is flowing, that is the direction of the charge flow, but the direction of the current flow is opposite. Now I can understand why the current is zero, because this is giving a current of magnitude to the right side, and this is giving a current to the left side. Although the charge is moving to the right, the negative charge, the direction of the current is opposite. They have the same magnitude, but the current is in the opposite direction. So what is the net current? Zero. Okay. Now let's go to this question. We have 8 coulomb of positive charges per second. That means 8 coulomb per second going to the right. So what is the current equal to? Let me call it I1 because of the positive. It is 8 amperes. Which direction? To the right. Charges direction, they are positive charges going to the right. So the current will be to the right. So let me take the right side as my positive direction. So I can say, instead of saying right, I can say +8. The current is +8 amperes. We also have some negative charges flowing to the left. So that current will be, let me call it I2. It is also 8 amperes. Is it to the right or to the left? Charges are going to the right. No, to the left. Charges are going to the left. So current will be to the right, opposite, because they are negative charge. So therefore, I2 is also +8. Okay, now we know the total current. So we have to add I1 and I2. I1 is +8. I2 is also +8. So I1 plus I2 will be 16. I1 plus I2 will be 16. So the answer is, and you again, I1 plus I2 is equal to +16 or -16? +16. Plus means the direction is to the right. So this. Question number 3. 325 kilometer long high voltage transmission line, 2.15 centimeter in diameter, carries a steady current of 1610 amperes. If the conductor is copper with a free charge density of 8.4 10 to the power 28, is there anyone listening to me here? Sure? If not, please leave. I would rather don't pretend that you are listening, okay? If you're listening, please listen. Otherwise, please leave. I'm not going to take attendance again. Okay, thank you. Thank you for staying. Let me continue. A 325 kilometer long high voltage transmission line, 2.15 centimeter in diameter, carries a steady current of 1610 amperes. If the conductor is copper with a free charge density of 8.4 into the power 28 electrons per cubic meter, what is the average drift speed of the mobile charge carriers? So when you read this question, okay, if you were paying attention to the lectures, you should know which equation to use. Here we are talking about the current and the speed of the charge carrier. So we had an equation in section 2, which is this. The current is related to the area, the cross-sectional area through which it is moving, and the drift speed of the charge carrier. So here we're talking about the drift speed, which is given. Oh, that is the question. What is the drift speed? So current is given to us. This is the current. N and Q, what are they? N is the density of the charge carrier. So here electrons, the negative charge, are the charge carriers, and density means how many charge carriers per unit volume. Okay, it is also given here. So many charge electrons per unit cubic meter, volume. And Q is the charge of one charge carrier. So that means charge of an electron. So given. So N is given, Q is given, I is given. A is the cross-sectional area through which it is moving. It's not given. Instead, it is given the diameter of the wire. If I know the diameter of the wire, do I know the cross-sectional area of the wire? Wire is like this, right? Like a cylinder. If you cut it, what kind of area we have? Circle. Do you know the area of a circle in terms of its diameter? No, pi r square. Okay, these things, it is not in the question. You cannot ask me, you didn't give it to me in the question. This is something that you are supposed to know. Area of a circle is something as engineers, as scientists, something you would be in your heart, okay? It's something like very basic, like 1, 2, 3. You should also know the area of a circle is pi r squared. Right. So let me continue. So now you know what to do. Instead of A, you will substitute pi r squared. But we asked for the diameter, right? So instead of pi r squared, you can say d squared over 4. Is that correct? R is the radius. What is given is the diameter. So radius is equal to diameter divided by 2. So r squared will be d over 2 whole thing squared. So it will be d squared divided by 4. Now my point is, in this equation, you can substitute what is given. N is given, Q is given, Vd is the question. A, instead of A, you have pi d squared over 4 and Vd. I is given, N is given, Q is given, pi. Of course, you have the button in the calculator. Don't use 3.14, okay? Use the button in the calculator. And D is your unknown. Is given. I'm sorry, D is given. This is the unknown. Vd is the unknown. So you can either do this, do algebra and make Vd as a subject and calculate it in the normal manner, or even better, use the calculator in the solve mode. Okay, I keep repeating this. One should learn how to use the calculator in the solve mode. Okay, that will save you time. Sometimes also, you will less likely to make mistake, provided you know how to use the calculator correctly. Number 4, when you flip a switch to turn on a light, the delay before the light turns on is determined by. Okay, so I showed you a simulation with the circuit, in the PHET website, if you remember that. When you put the light on, the bulb comes lit immediately, almost. It is, so it means, let me draw it. So this is the switch, this is the bulb. When you put this on, you don't have to wait for the electron from here, this particular electron, to come to the bulb and move through the bulb and get back to the battery. If that is the case, it's going to be a long time, right? Because the drift speed of the electron is very, very small. It is in millimeters, maybe a fraction of a millimeter per second. So it will take several seconds for this to reach here. Okay, the long wire if you're talking about. But that's not what happened. The moment you press the switch, the bulb is lit. Okay, immediate. That's because what we need to happen is the electric field in the battery to reach the bulb at the speed of light. That's what happened. The electromagnetic wave, the electric field, the moment you close the switch, the electron inside the filament of this, the wire of this bulb, will feel the electric field. It will come there at the speed of light, which is 300 million meters per second, not millimeters per second. So the answer to this is, therefore, there is a delay, but the delay is very, very, very small. Why? Because the electric field travels the speed of light. So what you need to happen, the electric field travels here. So that's why the light comes on almost immediately. So this is the answer. The delay is due to what? Due to the electric field to come from the battery to the bulb. So actually we feel that there is no delay at all. So now you understand why, because of the huge velocity of the electric field. But this is a straightforward question. Ohm's law. He is telling what is Ohm's law. If you have say a resistor R, and if you know the potential difference across this and the resistance of the wire, the current is given by the Ohm's law. I delta V is equal to I into R, or I is equal to delta V over R, or you can put it any way you like. Here, delta V is given and R is given. You are asked to find the current. So straightforward question. Okay, very easy. Question number 6. Again, very easy question. This is about the units now. Again, from the Ohm's law. Ohm's law tells me R, the resistance is delta V divided by R, I. And he is asking the ampere, which is the unit for current, is equivalent to what? So we can rewrite the equation for Ohm's law like this, and you can see ampere should have the same unit as the unit of delta V over R, which is volt per ohm. So that's the only one that is correct out of all these choices. Number 7, certain laboratory experiment requires an aluminum wire of length 28 meters and a resistance of this many ohms at certain temperature. What diameter wire must be used? So he's asking for the diameter, and the resistivity at that temperature is given. So this is the symbol for resistivity. He's asking for the diameter of the wire to have that much of resistance. Resistivity is given. So you should remember this equation where the resistance and resistivity is related. What is the difference between resistance and resistivity? Resistivity is the characteristic of the material. Okay, if you can take a copper wire, okay, and a long copper wire. A small copper wire, long. Both of them, because it is copper, have the same resistivity. This is the resistivity. But they have different lengths. Resistance will not be the same. The long wire will have the larger resistivity. Also, if we take the same length but thick wire, same length as this, but thicker, what is happening here? The area is changing. It is also the resistance is proportional to the length, but inversely proportional to the area. The proportionality constant is the rho resistivity. So when the cross-sectional area is big, we can have more charges flowing, right? Easily. So that means the resistance will decrease. More current mean for the same voltage applied. Okay, we will have more current flowing. That tells you the resistance has decreased. So this is the relationship. The resistance for a given material, that means rho is constant. When the length increases, resistance will increase. When the area increases, resistance will decrease, because the inverse relationship. And now I can answer this question. He is giving us R. He is giving us resistivity. He is giving us the length. We can find the area. But he's not asking for the area. He's asking for the diameter. And we are talking about a wire. The cross-sectional area of a wire is a circle. So once I have the area, I should be able to find the diameter, right? Area is equal to pi r squared, which is diameter squared divided by 4. So I get the area, then I can find the diameter. So please, this is not done for some reason. You know, I think I just went quickly without solving it, but you know, you should be able to solve it. Question number 8. So this is on the temperature variation of resistance and resistivity. So you can see when you read the question, a wire 2 meters long and 0.250 millimeters squared in cross-sectional area. So you are giving us the length, okay? You are giving it the area and the resistance at a certain temperature T0, the reference temperature. And he's saying the temperature is now increased to a different value T. And when you do that, resistance is changed to a different value. He's asking, what is the temperature coefficient of resistivity? So now you should immediately remember, in that section, we had an equation between how the resistance vary with the temperature, this equation. So here, so this is the reference temperature. What is the reference resistance? At this particular T0, the resistance is. At another temperature T, the new resistance. We have been given this, this, and this. All these four are given. We don't know what alpha is. So that is the question, find alpha. So substitute for the known things and we can find alpha. So again, please know how to use your calculator in the solve mode. That will save you time. Also, you will make less mistakes, hopefully, provided you know how to use the calculator correctly. Here, if you look at this question, these two are not used. It's not needed for the calculation. So this is kind of to check that you really understand the concept rather than trying to plug in the numbers to any given equation randomly in the dark. Question number 9. A potential difference across resting neuron in the human body is 82 millivolt and carries a current of about 0.340 milliamperes. How much power does the neuron release? It's a straightforward question. You're asking for the power, giving the current and the voltage, substitute and get the answer. Make sure everything in SI unit. Yes, the current is in SI. No, they are not in SI unit. I'm sorry. So this milliamperes, so you have to convert it into amperes. This is millivolt, so that you have to convert it into volt. Okay, finally, this is the last question in chapter 17 in this particular midterm exam. The other questions are on chapter 20. Okay, this is again about power, but added something to the cost. So he is telling there's a certain heater which has a power rating of 650 volt. That means when it's connected to the correct voltage, the specified voltage, it will draw an energy of 650 joule every second. But he is saying it is connected for 40 minutes. Then how much you should pay the electric company? The rate is given. If you use 1 kilowatt hour, you should pay 4 halalas. If you see how small the charge is, okay, well, I mean, the unit, if you have to use 4 kilowatt hour, that means millions of joules, to pay just 4 halalas. Okay, now, so that means, first of all, I have to find how many kilowatt hour you will use in 40 minutes. The energy is power multiplied by time, because power is energy divided by time. So energy is power multiplied by time. So let's find how much energy he uses in 40 minutes. So I'm going to substitute for power not in watts, but in kilowatt. Why? I want to get the energy in kilowatt hour. I don't want to get in watt second. I want to get in kilowatt hour. So then I can then go back to multiply by the rate and get the cost immediately. So let me get the energy in kilowatt hour. So this power is 650, but I converted into kilowatt. So it is 0.65 divided by 1000. And time is in minute. I have to convert it into hours. How do I convert the minute into hour? Divide by 60. So this is kilowatt, this is hour. So I get this much of 0.433 kilowatt hours we will consume if I use that apparatus for 40 minutes. Now he says, the electric company says, okay, if you use 1 kilowatt hour, you better give me 4 halala. But did I use 1 kilowatt? No, I use only 0.433. How do I get the cost? You divide by the rate. So 0.433 kilowatt hour, 4 halalas per 1 kilowatt hour, and there it is. So you have to pay only 1.7 halala for that particular usage of that heater for just 40 minutes. Okay, so that's it. If there is any question, I will answer. Doesn't look like any. So let me finish it. Thank you.